Hello, I am Michael Obina and welcome to my channel. Please subscribe to this channel, like and share to encourage you to make more of these videos. Alright, today we'll continue on our series on how to make flood risk map from results of machine learning, random forest and extreme gradient boost models for flood susceptibility analysis. In the last video I showed you how to use machine learning, random forest and extreme gradient boost to do flood analysis. Okay, and then we saw the result, and I said in this video I will show you how to generate the flood risk map. Okay, so we use Google Colab. In the last video. This is the programming we did, and we built our model, and then we got the results, the rock AUC, the accuracy values for random forest and extreme gradient boost. From there we got the rock curve, where we saw that random forest outperformed extreme gradient boost. From there we got our feature importance for random forest and for extreme gradient boost. So actually this feature importance, it tells us how the variables affect flooding in the study areas and their values. So this is the charts. But then the beautiful part of this code is that we were able to export those variables, those feature importance, as a CSV file, which was saved to our Google Drive here. Okay, and then we downloaded it to our local computer. Okay, I'm going to go ahead and open it in our local computer. So this is it. Okay, now in generating the flood risk map, we need these values. We need these values to generate the flood risk map. Now the beautiful thing about machine learning models against multi-criteria analysis like AHP is that in AHP we depend on expert judgments in assigning weights to variables in order to generate the flood risk map. So we relied on expert judgments, and this expert judgment could be subjective, it could be prone to assumptions, okay, and then some level of inaccuracies. And that's the beautiful part about machine learning, because machine learning is able to use the data sets you feed into it to learn the procedures going on the ground and then predict. So these values are actually as a result of the predictions from the models, and trust me, it is almost accurate. So these values are what we're going to use to produce the flood risk map. Having said that, let's proceed in making the flood risk map. I'm going to use an ArcMap 10.7.1. okay, so once you get here, you import all your data sets. These are my data sets. I've imported them. Okay, so one more left. Let me import the last one. So this is the topographic where there's indexed. I just brought it in. So I'm going to use symbology to adjust it up a bit, put it on classified, and then choose a better color ramp. I like this. Apply. Okay, alright, so this is my 12th variable parameter which I'm using to generate this flood risk map. As a preview, you can see them. This is the elevation, aspect is next, curvature, distance from river, distance from roads, drainage density, soil type, land use, land cover, rainfall, slope, stream power index, and lastly topographic wetness index. Okay, so now I'm going to reclassify all these variables using this scale. Very high I will assign 5, high 4, moderate 3, low 2, and then very low I'll assign the value of 1. So using this scale, I'll reclassify all those variables. So to do that, I'll come here and type reclassify. Okay, reclassify spatial analyst tool. I'll load it up. Alright, so input variable here. You can see all my variables are here. All my variables are here. So I like to work from the top to the one below. So I bring this in, topographic wetness index, and this is it. This is it. Now this is where I get to reclassify it into my 5 classes. But already here, the data set already has 8 classes. So I will have to, peg it down to 5 classes and then apply my scale. So I'll click classify in order to peg it down to 5 classes. Natural breaks, I'll leave it on that. It's already on 9 classes, so I'll peg it down to 5 classes. 5. Okay, this is the 5, and then I'll click OK. Now it's now time for me to assign weights. Okay, and this is it. You can see that the old values here are increasing. So I'll ask myself, does increasing topographic wetness index doesn't mean increasing flood risk? The answer is yes. Okay, so that is yes. So this value here is the highest. It means a high, very high flood risk. So I'll leave it at this. I'll choose the folder where I want to save it. Put it in training. Give it a name. I'll say reclass twi.tif. Save. Okay. I'll tick this and then okay. Let's run. Let's take some time to run. Perfect. So our TWI has been reclassified. So we proceed and reclassify others. The same reclassify. Okay. Pick the next variable, which is an SPI. Okay, do the same thing. Already this one is in 8 classes, so classify to peg it down to 5 classes. 5. Okay. So does an increasing value of SPI translate to increasing high risk flood risk? The answer is yes. If your distance is increasing, it translates to higher flood risk. So we leave it like this. We pick the folder where we want to save it. Is in this folder. We'll give the name reclass spi.tif. Save. Take this. Okay. Alright, so that's done. We go to the next one. We go to slope. Alright, it's already in 5 classes. So now let's assign a scale. Does increasing slope means increasing flood risk? The answer is no. Okay, no, because if the slope is gentle, there'll be high flood risk. But if the slope is higher, there'll be low flood risk. So we have to reverse this. So what it means is that where we have gentle gentle slope, which is lower slope, lesser slope, that is where we have higher flood risk. So where the slope is highest, that's where we have low flood risk. So that's why we reversed it. So we pick where to save this. We say reclass, let's go slope .if. We save to this. Okay. Alright, so we proceed to the next one. We put the next data set, which is rainfall. Okay, rainfall already has 8 classes, so we peg it down to 5 classes. Pick 5 here. Okay. So now we assign our scale. Does increasing rainfall amount mean higher flood risk? The answer is yes. Okay, so at this highest value here, that's what we're going to have the highest flood risk. So it is okay like this. Then we save it in a folder. We say reclass rainfall .if. We save it. See this? Okay. Proceed to the next variable. Go to land use land cover. Land use land cover. Okay. For our symbology, 1 stands for water body, 2 stands for vegetation, 3 stands for bare soil, 4 stands for agricultural soil, and 5 stands for built up. Alright, so which of these land use land cover classes has the least influence on flooding? That should be vegetation, and vegetation is 2, so it has to be, we assign 1 to it, followed by agricultural soil. Number 4 is agricultural soil, so assign 2 to it, followed by built up. 5 is built up, so assign 3 to it, followed by bare soil. Bare soil is 3 here, so assign 4 to it. And the highest land use land cover class that has the highest flood risk, that causes the highest flood risk, is water body. The closer water bodies to you, the higher the chances of the place experiencing flooding. So, and water body is the first one, number 1 here, so assign 5 to it. Alright, so we save it in a folder, we give it a name, reclass _LDLC.if. Save. See this? Okay. Alright, so we proceed by reclassifying other variables. So we pick the next one. The next one is soil, FAO soil. Okay, you can see it's already in 7 classes here, so we peg it down to 5 classes. Peg it down to 5 classes. 5 5. Okay, the FAO soil. Now this FAO soil runs from, the first one here is a sandy soil, and the highest one here is clay. Okay, so sandy soil, then we have silt, then loamy, before clay. So it is in that order. Okay, so which one has more flood risk? Okay, clay soil tends to retain water, leading to high flood risk, while sandy soil has a very high infiltration rate, so it allows water to pass, leading to low flood risk. So this will be the lowest and this will be the highest. So this order is correct. So go ahead, leave it like that. Save our raster. Say reclass soil. Save. Take this. Okay. Okay, so we'll proceed to the next. After soil, the next is drainage density. You can see that the class is more than 5, so we'll classify it, peg it down to 5 classes. Okay, so drainage density. If you have a lot of drainage, system in an area, it means more flooding. But less drainage system, less flooding. So this scale is okay. We're going to leave it like this, and then we continue. We save it. Reclass. Let's go. .if. Okay, and it runs. We proceed to the next variable. Next variable after drainage density is a distance from road. It has more than 5 classes, so we peg it down to 5 classes. We leave it at natural breaks. Peg it down to 5 classes. 5. Okay. Okay, distance from road. The closer you are to the road, the higher the risk of flooding. So the farther you are to the road, the lower the risk of flood. So we reverse this. We reverse it. Okay. We give it. We save it. If we take this, okay, perfect. We go to the next variable and classify. The next variable after distance from road is distance from river. It follows the same logic. So we will classify, peg it down to 5 classes. So the closer you are to the river, the higher the risk. The farther the river, the lower the risk. So we reverse this, and then we save. Proceed to reclassify others after distance from river. The next is curvature. Okay, you can see it's more than 5 classes, so we peg it down to 5 classes. Okay. So curvature. So at this side we have the concave and then convex. Alright, now the concave side has more flood risk and the convex side has lower flood risk. So we reverse, and then we'll give it a name. Proceed to other variables to reclassify. After curvature, the next we have here is aspects. It's already in 5 classes. So we reverse. Okay, so we will now do the last variable, which is elevation. Okay, so the least elevation has the highest height risk, while the highest elevation has the least flood risk. So we reverse, give it a name. Save. Take this. Done. Now, at this point, we have successfully reclassified our datasets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We have our 12 variables, all reclassified. So the next step is to use the results of our model prediction to assign weights and then develop a flood risk map. Okay, so we are going to develop one flood risk map. Why? Because our objective is to develop a flood risk map for the best performing model. So from the result of our model, we saw that random forests outperformed extreme gradient boost. So we will only produce one flood risk map, and that's for random forests using these values to assign weights to the variables. Alright, so let's get to that. And the tool we are going to use to do that, we'll use weighted sum. We come here, we type weighted sum, we search, and that is it. Spatial analyst tool, we'll bring it in. Good. At this point, we select our variables one by one. Select the next one. So we get all of them in. So we have all of them here. Let's cross check. 1 2 3 4 5 6 7 8 9 10 11 12. The 12 of our variables are here. Okay, this is where we'll now assign weights to them. So we go to the Excel. Remember the results of our random forests. So the first weight we are to assign here is elevation. We go here, we'll copy elevation, this elevation, copy, we paste at these weights. Next is aspects. Copy the weights for aspects. Next is curvature. Copy it and then paste. Next is distance from river. We paste it. Next is distance from road. Copy. Paste. Next is drainage density. Copy. Next is soil. Next is LULC. Next is rainfall. Next is slope. Next is SPI. Next is TWI. Good. We've imputed the weights, so we save it. Risk map.tif. Save. Then we run the tool. Running. Wait for it. Good. Alright, so it has run. This is the flood risk map, but you've noticed it's in more than 5 classes. So we have to reclassify this into 5 classes. So come back here. We type reclassify. And that's the tool, Reclassify Spatial Analyst tool. So we'll pick that layer, risk map. Yes. Okay. We peg it down to 5 classes. Okay. Give it a name. I like to give it the name flood risk map. Flood risk map.tif. See this. Okay. Alright, so this is our flood risk map. We can now use a better color ramp by using symbology. Come here, properties, symbology, put it classified, put it the 5 classes, and then pick a better color. To work with this, apply. Okay. Alright, you can see areas where we have the flood risk. The tick blue. I think I should use another color ramp to visualize this very well. To use this. I like to use this color. I like to use this color. Good. can see the areas where we have the flood risk. These are the areas where we have the highest flood risk, which is 5. These are the areas. One in red, and areas. So we can go further and edit our symbology and add our labels. Add the labels here. Okay, this is a very low risk. Very low risk. This will be low risk. Moderate risk. High risk. Very high risk. Apply. Okay, and it appears here. So areas where we have white, these are very low risk. Beside it, the blue are the low risk, the light yellow are the moderates, okay, the yellow, thick yellow are the high risk, and the red are the very high risk. Alright, so this is how to produce a flood risk map using predictions from machine learning models. I believe you enjoyed this session. Please like this channel, subscribe, and share. Thank you for your time.